Hello, welcome to your first chemistry video of 2021. One of Miss J's chemistry videos. I know you missed me. So this is going to be our first video in the topic of kinetics. It's topic 6 in IB. And it's basically the study of rates of chemical reactions. So we will be discussing learning target 11, where we will be able to describe how we measure the rate at which a chemical reaction proceeds. So it's nice to visit where we've been in IB chemistry thus far. There are really only 4 things that chemists really care about when we're talking about chemical reactions. And we've already talked about 3 of them. Even during distance learning, we've covered 3 out of 4 of these things. First thing that chemists care about is what substances are created during a reaction. Well, we've talked about this already when we talked about stoichiometry, and that's topic 1 in IB, and that was last year's learning targets. The number escapes me. So you've done this already. You can predict what type and how much of a product will be created during a chemical reaction. The second thing they care about is what is left at the end of a reaction when a reaction reaches equilibrium. And that is the study of equilibrium, which is topic 7. And we care if equilibrium lies to the left, meaning there'll be more reactants, lies to the right, meaning there'll be more products, or maybe at equilibrium, the number of reactants and products will remain the same. We also care about how much heat is released or absorbed by a reaction. And we just finished studying this. This was the study of thermochemistry, topic 5 in IB terms, and it was learning targets 4 through 10. So what's the one last thing that we really do need to care about when we're talking about studying chemical reactions? Not the last thing we're going to study in IB chemistry, but the one last thing, main thing that we care about. And that would be how fast or how slow a reaction will occur. And it's a study of kinetics, which is topic 6, and it's going to be learning targets 11 through 13 or 14, I believe. So we will see here that the speed at which a reaction occurs will depend upon the speed at which the molecules or atoms are moving, how many collisions occur between the particles that have enough energy to cause a reaction, and all of this is going to depend on the temperature and the pressure within a system. We've seen this simulation from PhET before, but it's nice to revisit it. Let's say we want a reaction to happen between 100 heavy particles like chlorine and 100 light particles such as hydrogen. As soon as I mix those things together, those particles begin to collide. Only some of those collisions will result in a reaction taking place. It all depends on how fast those particles are moving and if they're colliding with each other with the correct orientation. Now, I can increase the process and the probability of actually creating a product by increasing the heat in the system. And actually, before I do that, let's get our collision counter out. So I'm going to measure the number of collisions with the wall, which is kind of corresponding with the number of collisions of particles here, for 10 seconds. So before I increase the heat, there is 274 wall collisions. And if I increase the heat a bunch, and then look at those collisions, you'll notice that the number of collisions will have increased dramatically. And that's going to increase the probability that a reaction will occur. And of course, can decrease that probability by decreasing the pressure, by decreasing the volume, which in this particular case just allows the particles to float into the nether regions. And then when I measure the collisions again, there's not as many collisions that will have occurred. So why I'm showing this to you is just a reminder of the interdependence of heat, pressure, number of particles, and the velocity of those particles in order to make a reaction happen. One last thing about this, The big particles and the little particles here all have the same amount of kinetic energy because they're all existing at the same pressure and volume. However, because they have different masses, they will have different velocities. Thinking back to physics, kinetic energy equals 1/2 times the mass times the velocity squared. All right, what units do we use and how do we define reaction rate? So reaction rate is defined as the change of concentration of reactants and products per second or per minute. I have a typo right there. That should be right there. That should be or per minute. Whoops. So what we're going to see here is that the standard units for reaction rate is the concentration, moles divided by liters, per second. And that's why seconds is in the denominator here. This notation would be for standard units, as if you were a US student writing this. But IB prefers those metric units of moles per cubic decimeter times seconds, where these will be all in the denominator, or you'll see them where you will have a negative exponent, meaning decimeters cubed is in the denominator here. Seconds is going to be in the denominator as well. One last thing about this, which is really important, if we're measuring a gas, a reaction that creates a gas, concentration of a gas is proportional to the volume of a gas, according to Avogadro's law. So we could also have here a change in volume, and that would be another way we could measure reaction rate, as you will see on this next slide. So what I've got going for you here is I have 4 videos that are going to show you the 4 different ways that we can measure reaction rate. So we can measure reaction rate either by measuring the change in mass or volume that occurs during a chemical reaction. We can change the pH in an acid-base titration, and by finding that change in pH, we can actually measure how long it takes and therefore the reaction rate. We can measure the change in conductivity. We haven't gotten into electrochemistry yet, but we're going to get there, and that will allow us to also figure out a way to measure reaction rate. And last but not least, how to measure color change, or how quick or how slow a reaction's color change will occur will dictate the reaction rate. So let's go back to this one where we're taking calcium carbonate and hydrochloric acid. This would be the one we're going to do with our simulation that's going to occur after this introduction to kinetics. This student has calcium carbonate in a flask, added to it hydrochloric acid. What's going to happen is you're going to create some hydrogen gas and calcium and carbon dioxide from this reaction. And the gases that are created are going to be collected into the balloon. I'm going to zoom it up here to about this time, and you'll see the balloon has inflated. And how long it takes for that balloon to get to a particular volume is going to dictate the reaction rate of the 2 reactants to make products. So reiterating how we can measure the change in pH to measure reaction rate. We did this titration simulation last year. You've never done it personally, unfortunately, because of the pandemic. But what this scientist is doing is increasing the pH of the acid that is in the flask very slowly. And they will know that it has turned neutral or basic once the phenolphthalein will turn pink inside that flask. How long it takes to do this and how many drops it takes will dictate reaction rate, or how fast the reaction actually occurred. So change in conductivity, we haven't talked about this yet, but basically think about building a battery and how fast a battery will conduct a charge. This is called a galvanic cell. In this side, you've got some zinc sulfate. On the other side, you've got some copper sulfate. And this has a copper lead in there and a zinc lead. And you'll learn why this works a little bit later on. But this particular reaction will occur. However, you won't see the chemicals being mixed together. You just know that this reaction will be occurring because there will be a change in the amount of ohms, the energy or conductivity that will be measured from the multimeter there. And then the last way we can measure reaction rate is how quickly or slowly a reaction changes color. And I'll just let this one play for you because there's some pretty color changes that occur. Caustic soda is the same as baking soda. The lower the concentration, the slower this would turn. What colors appear when depends on the rate of reaction of the different species involved. So that's called a clock reaction, and I wish we could do that one in real life. Sadness again. So this is going to be the end of the first initial introduction to kinetics. Where we're going to next here is we are going to analyze the effects of concentration on a reaction rate. So I indicated that during the color change video that the higher the concentrations, the faster your color change would occur. And also the speed of the reactions dictated what colors appeared when. We're going to do this in a more simplistic format where we are going to look at the reaction of magnesium and hydrochloric acid. We're going to perform a pivot simulation where you are going to virtually drop some magnesium ribbon in various concentrations of hydrochloric acid and measure how fast you can move the stopper here from 5 milliliters to 20 milliliters of hydrogen gas. So to show you how this works, I am going to first show you that you have a variety of different trials with different concentrations. The first one we are going to do is 2.2 moles per liter. We're going to load that one up. And then the first thing you want to do when you do this simulation is you're going to want to hit play You're going to want to hit play and move that plunger inside of the inside the syringe to 5 milliliters. So off I go, putting the magnesium in the graduated cylinder, and it goes a little bit fast at a higher concentration. So I'm going to back it up, and every mark here is 5 milliliters, and it's about right there like that. You're going to want to have this stopwatch turned on. And as soon as you've moved that plunger within the syringe to 5 milliliters, you're going to want to reset the stopwatch. And then you are going to hit play, or you can fast forward through until that plunger reaches 20 milliliters. So this one's going to go fast. I'm going to just step it through here. There's 10, 15, 20. So there's going to be some questions down below that's just going to make sure that you are performing the simulation correctly. Your data might be slightly different than what the answers are for the multiple choice, but choose the number that is as close as possible because the other three choices will be completely way off. You're going to collect some data. You're going to manipulate the different concentrations of hydrochloric acid, and you're going to compare those to the how long it takes to go from 5 to 20 milliliters within the syringe. You're going to graph like you did last time, and you're going to use the curve of best fit. Hit that button and play around with these different mathematical formulas until you find the curve fit that fits your data most appropriately. I will give you a hint. The answer is not linear. So then they'll have some questions to answer after that. And this is your introduction into kinetics. So hopefully this all made sense to you. Of course, I will always be available to have questions. Have a good evening.